I'm going to present process integration in semiconductor manufacturing. Basically, I'm Dr. Akhilesh Pandey, scientist working in solid state physics laboratory. There is a lot of problem I have find out during the for the network. So first of all, I will tell about the semiconductor materials and device market. India is now there is a semiconductor mission in which semiconductor materials in North India it is around 23%. In the global market, it is around 230. It seems that the US global market comes to be 189. Or Indian semiconductor market, you can see starting from 2022, it is $26.3 billion and it is increasing every year. It is expected in 2032, it will be around $271.9 billion. So semiconductor, a lot of applications of semiconductor in military and defense applications. Recently, Tata has three major projects have been launched by the Tata. One is Gujarat, two is Gujarat, Dharara and Sanand, and third one is Now, steps of the semiconductor process, basically the process growth and wafer fabrication and its characterization. Semiconductor layers can be grown using the epitaxial techniques, and its characterization can be done in the semiconductor processing. Semiconductor device fabrication and device characterization is also very important, and device packaging model. And incorporation after packaging, it has to be incorporated into the system. Now, the plan of my talk. First, I'll tell about the introduction, in which I will slightly touch up about the semiconductor materials and devices, where the various products have been fabricated. Semiconductor devices have been fabricated. Bulk crystal growth, in which I will slightly cover the bulk crystal growth technology using Bridgman-Choklowski PVT growth technique for silicon carbide crystal, which is a wide bandgap material and highly utilized in the various power devices. Wafer fabrication techniques, because it is also very important, because wafer has to be fabricated in a very good way, so that it can be used for the epitaxial layer. Now, semiconductor device processing method, in which lithography, photolithography, etching, ion implantation, and deposition. These are the process which has to be involved for fabricating semiconductor devices. Now, as far as introduction is concerned, now you can see that there are several. Several technology which is useful in the semiconductor devices. Basically, the semiconductors, either it is an elemental semiconductor or it will be a compound semiconductor. And in the elemental semiconductor, basically silicon and germanium, there are two semiconductors which is widely used for fabricating devices. Compound semiconductor, basic inorganic semiconductor, there is a gallium oxide, cadmium sulfide, zinc oxide, copper oxide, gallium arsenide phosphide. Inorganic semiconductor is also utilized for anthracene, tetrazene, and polypyrrole. And there are two types, intrinsic or extrinsic, as everybody knows. And for group 4, basically carbon, silicon, germanium, group 5, 3,5 and 2,6, mercury, cadmium telluride, cadmium zinc telluride, 4,4, lead, SN and TE. These are the several semiconductor materials which are technologically used. Now, as for a 3-5 semiconductor, basically 3-5 semiconductor, group 3 and group 5. Either it is gallium arsenide, aluminum arsenide, or gallium indium arsenide, and for 3 and arsenide, phosphide, and terminites, and mixed anions. And nitride, I can include nitride here because what happened, aluminium, nitrogen is also in the 5 component, but 5th group, but it is now widely used as a nitride material. And the 3-5 semiconductor, basically either it can be used for high electron mobility transistors, microwave devices, lasers, for green lasers and high wavelength lasers, LEDs, solar cell, single photon source detector, photo detector. These are the common applications using 3-5 semiconductors. And this is the energy versus lattice constant. Lattice constant, where you can see how it is changing. Now, in the common semiconductor, silicon semiconductor, 2,6 semiconductor, cadmium zinc telluride, mercury cadmium telluride, zinc telluride, 3,5 semiconductor, gallium arsenide, gallium antimonide, 3 nitride. Right now, the silicon carbide is also for power device application, germanium semiconductor, which is IR semiconductor, 2D semiconductor, graphene MOS2 semiconductor, metal oxide semiconductors. Now come to the bulk crystal growth technology and substrate fabrication. Bulk crystal growth for fabrication of substrate for epitaxial growth devices. Basically bulk crystal growth technology. First, one has to synthesize the raw materials, then crystal can be grown, then fabrication of bulk crystal growth fabrication, proper shaping, size, crystal cutting, lapping, polishing, then characterization of the bulk crystal. Then after characterizing desired application for epitaxial growth, or sometimes it can be used as a substrate also. Now crystal growth technique, there are 3 types of growth which is commonly used. Growth from metal, growth from solution, growth from bulk, growth from melt, growth of solution, growth from vapor. In the bulk growth between Bridgman, vertical gradient freeze method, traveling heater method, Chokladky float zone, and growth from solution between liquid with epitaxy, which is very commonly used to grow the epitaxial layer, very thick epitaxial layer, maybe 10 micron or more than that. Sometimes low thickness can also be grown using liquid phase epitaxy. Growth from vapor, basically MOCVD, MBE, PND, and sputtering. Shall I go for next slide?
Yes, sir.
We'll now come to the bulk crystal to wafer fabrication. Basically, for bulk crystal to wafer fabrication, raw materials of a polycrystalline material has to be kept onto the crucible. Then in the Chokladky method, Chokladky growth method, either it is rotating and pulling at a certain temperature above the melting point, and large area growth can be possible. And after growing this bowl, silicon crystal can be cut, and cutting or slicing by the wire saw. Then this wire saw has to be fabricated for the microelectronic circuits and devices. Now this is the Chokladky process. This is silicon Chokladky process. Now raw material of silicon polycrystalline has to be kept into the furnace. Then this is quartz crucible will be there, and this single crystal silicon, again it is a seed crystal inserted below that one. Then crystal pulling and rotating, these 2 phenomena is occurring, and these are some parameters like crystal pulling. Chokladky process time should be around 18 to 24 hours. Temperature more than 1300 degrees centigrade. Pressure 20 torque. Pulling 0.7 mm per minute. The advantage of this Chokladky method is large size single crystal, high growth rate. A seed is inserted into the bed. Pulling and rotating simultaneously. Seed a crystal diameter controlled. Diameter can also be controlled by the temperature. After growing, it has been sliced, and this is the final device of the fabricated wafer, on the fabricated wafer. Now in the Chokladky, using the germanium crystal growth technology, germanium can be grown by CZ method. Then again crystal cutting, slicing, and the things can be fabricated, wafer can be fabricated. Now come to the Bridgman growth. In the Bridgman growth, what happened? Liquid solid growth technique. Here melt has to be have been made, and melt lowered through a linear temperature gradient. The crystallization is occurring. This is the temperature gradient phenomena is occurring. Lowering the thermal gradient is required by control cooling. And in the Bridgman method, basically main advantage is faster growth rates are possible, large size area crystal can be prepared, better crystalline quality. But sometimes dislocation density is high as compared to CZ method. Growth rate is slow and various crystals can be grown using this one. Now float zone. In the float zone method, what happens? It is a technique by growing the crystal without crystalline. So what happens? The single crystal can be grown. There is a single polycrystalline silicon rod will be there, and there is a RF heating coil can be kept onto the center, and one can create a molten zone. A molten zone is held in the place between two solid rods by surface tension, and this rod is moving. And by moving this rod, a seed crystal is dipped onto one end of the zone and zone of the molten zone, move towards the feed stock to grow the single crystal. Basic advantage of the float zone is because it is a crystal free, the purity is high, and one can dope it. And limitation because the diameter is low, but it is a very important technique because the purity is very high. So in the case of silicon, there are not any oxygen component is very low or maybe minimum. Now this is the wafer fabrication technique. First the crystal can be grown and single crystal ingot will be there. The crystal shaping, trimming and this diameter is grind. And after grinding, it's a flat grinding will be there, primary and secondary flat. Then wafer slicing. After slicing, there should be edge rounding, then lapping to make the sample up to the so that the roughness should be less than 2 nanometer or 2-3 nanometer. Then wafer etching, polishing. After polishing, its roughness is very less, maybe 1 nanometer or 2 nanometer. Lapping it after lapping, the roughness is maybe 10 nanometer, 20 nanometer. Then wafer inspection is also very important. It is a epi can be grown in this wafer or not. So these are the some processes of the wafer fabrication technique. And here you can see that wafer fabrication to device processing to assembly. Wafer is this is a single crystal ingot. Am I audible?
Yes, sir. Yes, sir. Audible, sir.
You are moving the slide, sir?
Yes, sir. I'm moving slide also. I hope everybody is audible.
Yes, sir. Audible.
Yes, sir. Audible, sir.
Audible,
Audible, sir.
Yes, sir. I am changing. As per your talk, I am changing.
Yes, sir. Audible. Even slides are changing, sir.
Slides are visible or not?
Yes, slides are visible and now the voice is not coming.
Visible, sir.
No, everybody getting voice or not?
Yes,
Yes, sir.
but not
Yes,
now.
Okay. Then it is fine. You can go ahead. Sir, go ahead, sir. No problem.
Yes, sir. Not getting the sound, sir.
As discussed with you today, we have modified the EL and visible criteria as well as
This
including
testing has been done. This is the whole process of the wafer fabrication. wafer fabrication to device processing and up to assembly and testing, which we have to do. Which one is we are doing. Now with the bulk single, now come to the bulk single silicon carbide crystal growth by PVT method and its wafer fabrication. The silicon carbide polycrystal source is there. It has been heated so that the vapor is transported, and there is a silicon carbide bowl. Silicon carbide seed crystal will be there, and silicon carbide bowl have been formed. The bowl have to be cutted by the wire shop and shaping, wafer surface grinding, chemomechanical polishing. This is the final wafer, and this is the atomic force microscope where we can check the surface quality of the silicon carbide wafer. Now this is another diagram. One can see that while doing the silicon carbide, growth window is very less, because for 4H silicon carbide, growth window is around, this is the growth window around 200 to 21 to 2200 degrees centigrade. And the stacking fault of various polytypes are very, there is not very difference is very less between the stacking fault energies of the 4H, 6H and 15R silicon carbide. So any impurity occur while doing the silicon carbide, what happened? It is a finite possibility that either another polytype like 6HSIC or 15R has been grown. So for temperature should be highly stabilized, and carbon to silicon ratio is also very important. So to reduce the foreign polytypes, temperature stability, carbon to silicon ratio is very important. Now, polytypes inclusion, this is one of the example which I am explaining here. After growing the silicon carbide wafer, this is a silicon carbide wafer. Axis-Hawkinger measurement have been done at several places. We have identified using here either it is 6H or 4H. Then what happened? Its X-ray diffractogram has been done. In the 6-4H, what happened? Apart from 004 and 008 peak in theta to theta again, another peaks will be there. These peaks are kinetically absent peaks. But what happened? Using the slow X-ray diffractogram, these peaks are visible. And using this phenomena, we have identified the region of the 4H silicon carbide region. And another region, what happened? Another X-ray diffractogram had been done, and we found that it is 006 and 0012, and other peaks are 0015 and 0015. This is showing the 15R peak. And several small peaks are kinetically absent peaks have also been identified, and it is confirming that 6 and 15R is present. So this is the identification of satellite peak. The basic importance of this peak is what it should not get, but due to spatial structure of silicon carbide, this is natural superlatives, we are getting these peaks, and it can be used for identification of various silicon carbide polytypes. So in the single crystal, in one crystal, what happened? We have the 2 theta omega scan by changing the position of the crystal. When I identify and by finding out the lattice parameter, one has also identify the lattice 6H, 4H and 15R polytypes. Now we did the X-ray topography to find out the various polytypes. X-ray is falling on the crystal as a tracing incidence angle. It has been the plane which we have been kept, that is 4H118, and X-ray topography mapped the intensity of the reflected beam, and image contrast shows the local imperfection in the crystal. To get large area exposure, tracing incidence plane is used. Now one can see that the 4H, 6H and 15R, all the peaks have been identified. All the topographs have been identified. It is showing the confirmation of polytype present into the crystal. Now, further confirmation, Raman spectroscopy have also been done using the laser excitation of 532 nanometer. We have identified 6H, 15R and 4H. These peaks are identified. The optical pronouns of 4H SIC, 6H SIC and 15H SIC exhibit the 24, 26 and 27 modes respectively. 4H SIC and 6H A1 is the axial mode and E1, E2 are the planar mode, while 15R A1 and E modes are the prominent. And In the Raman spectroscopy, several these red spots has also been identified. These spots show that there are multi micropipes present into the crystal. Now, X-ray pole figure analysis have been done for the bulk zinc telluride crystal. While growing the zinc telluride crystal, what happened? Crystal had been known, but we don't know what are the orientation, and our requirement is for 110. So for that, we did the X-ray pole figure measurement. X-ray pole figure measurement, basically in the 110, there are seven spots has to be present. So these 7 spots, but we are getting a lot of spots. Then how it can be cut? So first, it has been highest peak has been taken, that is 220, and apart for the 220 family or 110 family, 7 spots have been identified. But other spots will also be there. So what happened? We have identified another second stop and another 7 spots have been identified. It means it is showing there are 2 grains are present, and taking 1 grain crystal have been cutted. And after cutting the X-ray pole figure measurement have been done, we found that these 4 peaks are these 4 peaks are which is expected these 2 peaks. So we have by just taking the proper tilt angle using the X-ray pole figure method and rotation angle, crystal has been cut and found that the crystal is highly oriented along 100 direction. Its X-ray diffractogram confirmed that crystal is cutted. So it is very important characteristic technique to cut the crystal in a orientation cutting. And its PL measurement also shows that there is a defect emission and bandage emission have been identified. Now, come to the semiconductor device processing. In the semiconductor device processing, the things first, the device processing lab should be in the clean room. A clean room, either it is a 10,000 classroom, 100 classroom, or 10 classroom. It has to be clean room, and depending on the device, the clean room class has to be changed for the processing room. And surface preparation. Surface preparation is also very important because mechanical and chemomechanical polishing has to be done. And using chemical and chemomechanical polishing, surface preparation is very important to grow the to fabricate the device. Then metallization and dielectric coating. For metallization, one can use the thermal and evaporation, and dielectric coating, one can use the either sputtering, CVD. These are the several techniques where the dielectric coating can also be done. Now, photolithography, there should be mask aligner and spin coating. There is a rinse coating. The spinners should be there. Mask fabrication, laser interpreter will also be there, and etching, either it is a wet chemical etching or dry chemical etching. Reactive and dry chemical etching, basically reactive ion etching or DRI. These are the dry etching. Now, in the semiconductor device fabrication process, basically these are the steps which has to be used for the final device up to the test assembly. First, the device has to be designed properly. Then, after designing, the wafer preparation. Wafer preparation means whatever the wafer we have, it has to be finally come to the proper epi ready wafer. After growing the epi ready, the front end process can be done. In the front end process, what happened? Photolithography, etching, cleaning, thin film, dielectric metal deposition, ion implantation. So suppose if we are making a PN junction diode, we have an N-type substrate. So make it P-type. The ion implantation can be done. Then ion implantation, then ion reduction, then annealing. After annealing, activation annealing, then planarization. Then the chemomechanical paralysis will be there to make the surface planar. Then flip chip bonding, wire bonding, then testing and assembly. These are the common fabrication processing steps which has to be involved while fabricating the final devices. Now, in the designing, basically what happened? Device can be designed, circuit designing, stability designing rules, circuit elementary design, interconnect routing, device simulation, pattern preparation, mask preparation. For photo mask designing, a photo mask is a template used in a semiconductor production, especially in a photolithography. It consists of transparent material. Example is a glass, parts, or a special structure on its surface. Basically, mask designing software, the basic software is K-Layout, which is freely available, LED, AutoCAD. These are the common mask design software. There are several other designing software is also there, but people are used, but they are sometimes they are costly, and this is the one of the mask which has to be used in the lithography. The wafer preparation, substrate cleaning, and NAP wafer, that is also very crucial and important. Now the lithography, photolithography. What is the meaning of the lithography? Lithography means literally writing a pattern in stone. Just it is a common answer of this common you can say definition of the photolithography. The photolithography requires UV light source, photo mask, which I explained in the previous slide, optical exposure, whatever the mask
slide is not visible, sir.
Pardon, sir. Slides are not visible.
1 minute. Slides, sir.
Not visible, sir.
Not
Yes, sir. You
visible,
are
sir.
audible. They're telling slides are not visible.
The audio is coming,
Sir,
sir.
Slide visible, sir. Visible.
kindly share slide once again, sir.
Visible, visible.
The slides
Slide
are
No,
is
sir,
visible,
it is
sir.
not visual, sir.
No, no, it's
Not
It is
visible.
not
sir.
visual.
It's visible, but it is in a Raman spectroscopy.
Sir,
Slide name not knowing, sir.
slide is already shared.
No, it's
Slide
visible.
visible, sir. Some members
Seen
not
in
visible.
still Raman spectroscopy.
Low bandwidth.
Slides are
No bandwidth,
Raman
not visible.
spectroscopy only, not changing. Slides are visible. Slides visible only. It's in Raman spectroscopy only. It's not changed.
Yeah, slides are visible and changing also.
No, sir. Here only Raman spectroscopy.
No, sir, it's not visual.
Slides not changed. It's in Raman spectroscopy only.
Tangavel sir, your screen is paused now. Tangavel sir? Can you hear me?
Hello, sir. Can you hear me? All the participants, please wait for a second. I guess there is an internet connection issue in sir's cabin. I'll go and check.
Sure, sir, sure, sir.
Okay, thank you, sir.
Okay, sir.
Now it's visual, sir.
Now it's visible.
So in which slide I have? I am in this one photolithography slide. Slide number 26.
Yes, sir. Yes, sir.
Now come to the lithography part. In the lithography,
Sir, yes,
means the basically definition of the lithography, writing a pattern in a stone. The photolithography requires a UV light source. A UV light source, photo mask, optical exposure system, and what happened? Am I audible, Thangamal? Audible?
Yeah, audible, sir. Audible.
Yes, sir.
Now come to the lithography part. In the lithography means literally writing a pattern in stone. Photolithography requires UV light source, photo mask, optical exposure system where the exposure can be done, photoresist and developer. Then after that, photoresist. Photoresist, basically this is the radiation sensitive material which can be used for the pattern transfer to the wafer. It consists the resin and sensitizer. Two types of the photoresist will be there. Either it is a positive photoresist or negative photoresist. In the positive photoresist, what happened? There are no in the photo mask. What happened while fabricating the? Hello, I'm audible. I'm audible.
Yes, sir,
Yes,
you
yes,
are
sir. You
audible,
continue,
sir.
Continue, sir. Audible, audible, sir.
Angamal, I'm audible.
So
Yeah,
you are.
audible, sir. Audible.
Thank you, sir.
Photolithography, audible.
Now what happened in the this one photo mask? Basically, photo mask either it will be bright field or dark field. In the bright field, what happened? Where the metallization can be done, suppose if you have to deposit the metals or that will be in the dark field. In the bright field, apart from other area, it can be deposited. So now you can see that this is the exposure is this is the exposure and this is the mask. Now you can see the negative resist. The apart from this is the resist and other are vacant. In the positive photoresist, the vacant portion are there and these are the photoresist is there. So what happened? Now the process of lithography, basically first the resist has to be coated, photoresist has to be coated onto the oxide substrate and SiO2. Then exposure, deep UV light exposure will be there. This is the optical lens and the photo mask. This is the photo mask with the opto-clear patterns. Then development, after exposure, it has to be developed. The photoresist makes where the exposure will be there, the photoresist will be weak, so it has to be removed. And in the negative, no sorry, other portion are weak and it has been removed. And the negative photoresist resist where the other portion of photoresist will be there and this is the removed. And this is the after this one, the etching and resist stripping has to be done. Now the photoresist coating, basically a spin coater will be there, in which the resist material has to be dispensed. Then sample has to be kept and spinning and coating the photoresist. After photoresist, it has to be using the mask aligner, the lithography and aligning of the mask at a particular place. While fabricating the photo mask, some alignment mark will be there for one step. Another step, that an alignment mark should also be used. Using this mask aligner, mask has to be aligned. Now alignment and exposure, first transfer the mask image onto the resist coated wafer. Now this one, the UV light source, and this is the mask, and UV light has been exposed, and this resist will be there. And UV light exposure, now you can see that the chrome island on the glass mark, and this is the photoresist material. This is the photo mask, and this is the exposed area. Then after exposing it, its resist have been removed, and this is the window where the other fabrication has to be done. Now, three types of exposure will be there. One is the contact aligner, where the photo mask has to be kept onto the substrate. Another is a proximity aligner, where it is a less wear mask but poorer image than other contact layer. In projection aligner, it will be far from the wafer. Now the lithography resolution, basically resolution depends on the wavelength which is exposed, and it depends on the R is greater than K alpha, where alpha needs to be minimized and K will also be reduced. And for it has to be large aperture, high quality lens, small exposure field, step and repeat using stepper. Optical proximity correction should also be there, and phase shift mask will be used. For lithography is difficult and expensive. There are 40 lithography steps. Of course, if you are making any of IC, there are 40 lithographic steps will be there. Using these steps, the IC processing can be done. Now, other lithographic technique, apart from the photolithography, there is a electron beam lithography, where electron beam scans the exposed electron resist onto the wafer, and it is a ready technology with relatively low throughput, but it is a very high costly. Electron projection lithography expose the complex pattern using the mask and electron lens similar to the optical photography. Nano imprint, where the patterns are etched onto the durable materials to make the stamp just like a stamp. This stamp is pressed into the liquid film over the wafer surface, and wafer liquid is hardened with the UV to create an imprint onto the fine pattern. So these are the electron beam lithography, dipple lithography, nano shaving, nano grafting. These are the several other lithography pattern which can be used for the nanotechnology. Now, pattern transfer. Pattern transfer, basically after growing the SiO2 and after exposure, it has been developed, and photoresist will be there. Photoresist developing, you can see this is isotropic etching will be there. This is the etching proforma. Now you can see the near the below this SiO2 it is isotropically etched the whole area. Now resist has been removed. These are area where one can use for the fabrication process. Now for anisotropic etching, what happened? Photoresist will be there, but etching is the etchant which we are using, that is a anisotropic etchant. So it can be remove the vertical pattern, and these are the vertical pattern which has been etched. It can be used for the fabrication of the devices. Now in the etching is nothing but it is is defined as a removal of the surface material. The agent used to do etching is called etchant, and depending upon the physical state of the etchant, and there are two types of etching: wet etching and dry etching. In the wet etching, what happened? Liquid etchants are used, and no liquids are used in the dry etching. The main application of this etching process is transferring the photoresist pattern onto the wafer substrate, preparation of smooth pattern to the wafer substrate, preparation of smooth damaged free surface for epitaxial growth, producing clean residual free surfaces for subsequent device fabrication, to study the defect structure of the semiconductor and form the measure
So
structure.
slides are not moving, sir.
And
Slides are
transfer
not
the
moving.
submicron dimension on wafer surface with controlled undercut.
Sir, Agle sir.
Surface via
Slides are
hole
not moving.
via hole and for grounding. Now, basic concept of etching. Etching etching is the process of removing the material in a specified area through a wet or dry chemical etching. Basically, in the etching is nothing but it is similar to the chemical vapor deposition, but except the material here the materials are removed. Here, what happened in the etching process? The etchants has to diffuse onto the film, and it has reaction will be take place, and it has been transported and mass transported reaction product and byproducts of the reaction has to be come out from the wafer. Now, in the etching technique, basically, I tell you two types of etching. This is wet and dry etching. So, remove the barrier material protected by the hardened of the photoresist mask, and it has a high degree of selectivity required. And depending on the source used in the etching, basically wet chemical etching, immersion or spray, and dry etching, plasma etching, or reactive ion etching. These are the dry etching. Now you can see that the etching process, first deposition of the film on the substrate. And a photo mask will be there, and photo mask then exposure of the chrome mask using the UV light, and after that it has been developed. Photoresist will be removed, and then etching of this deposited film. After etching, one can see these are the pattern have been formed, and then remove the resist. After removal, this pattern is formed. This can be used for the fabrication. Now, wet etching and dry etching. In the wet etching, basically it is an isotropic etching, basically normally, but in a dry etching, it is an anisotropic etching. So both the etchings can be used, but if you use the selective etching, then wet chemical etching can also be cut into the vertical direction. Now, etching profile basically depends on the etching and isotropy, where etching anisotropy, EH is a horizontal etch rate, EV is a vertical etch rate, AF lies between 0 and B. AF is a H anisotropic factor. Basically, if AF is 0, 1, isotropic etching. If AF is less than 1, directional etching. If AF is equal to 1, it should be vertical etching. So, various factors which depends on etching, that is the etch rate, which is slow, moderate, fast, etch profile, nature of the etched surface, selectivity, stability of the masking material, in which mask photoresist dielectric metals are used. Wet etching, basically in the wet etching, the etching process involved in the transport reactant to the surface reaction will be there. Basically, the advantage of the wet etching process, it is a low cost, reliable, high throughput, excellent selectivity, and various disadvantages will also be there. Very hard to control the critical features of the emission, difficult to control the degree of over etching due to undercut, decrease the etch rate as a reagent solutions are consumed. Now, interconnect metallization, that is also very important, where the interconnect metallization in the etching process, basically photoresist have been used onto the metal. And now, this in the etching process, in non-selective etching, this metal have been etched. This is a metal etched, and then photoresist have been removed. But it is a non-selective etching. So our metal is not into the you can say cubical or cubical format. It is not a selective format is different. But in the selective plating, what happened? First metal has to be there, then selective plating, then gold has been deposited, gold have also been deposited, then photoresist have been removed, and apart from photoresist and metal, some etching of the metal will also be there. So it is the interconnect metallization using this process. Now, dry etching. Dry etching are those which can be used with the plasma driven chemical reactants. The basic advantage of dry etching, any material can be etched, and reduce the undercutting with high etch rates, capable of patterning smaller geometry, feature of order of micron or less than, a very good dimensional control, purity can be higher. And basic disadvantage, the complex dependence of the process results on the process parameter, many damage the active layers, less selective heating. Dry etching is commonly used for etching during the fabrication, like silicon gallium arsenide based devices, gallium arsenide based high frequency devices, gallium nitride and silicon carbide based high power devices, as silicon nitride, SiO2 dielectric films. Basically, in the dry etching, plasma etching or reactive ion etching can be used, which is an isotope. Now, this is the scanning electron microscope, the view of the plasma edged 0.16 micron millimeter pattern. You can see that these are the pattern which has been done. Now come to the doping. The basically two types of the doping can be done to make either N-type substrate P-type or P-type substrate N-type. One is the ion implantation and another is the diffusion. NAND implantation, what I meant, which is a very, and ion has been implanted, and after implantation, it's a some lattice damage will also be have to be done. So annealing will required to activate the dopant, but it is a good control of implantation depth with energy keV to MEV, and repair the crystal damage by using the annealing, which can be cause the dopant diffusion or also the loss of some time depth of to control. And the diffusion can be done.
Everybody has see, sir. 1 minute, sir. Everybody has see slide, sir.
And there is also phenomena, but the control is slightly less.
No, sir. Not visible, sir.
Not visible. Just 1 minute.
You can see that whatever the ion you have to deposit, first ion source had to be generated.
Now visible, sir. Dry etching.
Ion imaging magnetic path where the
Dry etching visible, sir.
Phenomena have been used. Char to mass ratio have been collected, and it will pass the path, then accelerated tube where the has been applied so that the carriers, or you can say second ions or carriers have been accelerated, and there is a XY plates and there is the wafer where the implantation can be done. And the silicon, beryllium, boron ions have to be implanted to make the silicon. Now, other doping technique, gas source doping, where gases has to be collected, doping can be done. Solid source doping, dopant diffuses from the doped solid film. In situ doping, dopant is controlled, introduced while the silicon film is being deposited. Ion implantation, after ion implantation, thermal annealing is very important, and the furnace annealing takes minutes and causes too much diffusion of the dopant some application. So the RTA is very important, which can be used for the controlled annealing. Now for the deposition, basically two types of deposition basically used. One is chemical vapor deposition and physical vapor deposition. For MOSFET, gate dielectrics, metal dielectrics, for interconnect, dielectric deposition of metal layers, encapsulation of IC, these are the deposition steps have been required. Two types of the CVD technique, basically LPCVD, low pressure CVD, or plasma enhanced CVD, where the this dielectrics materials can be deposited. Now the chemical vapor deposition, where the precursor chemicals passes through the using the path, and it will be reacted onto the silicon wafer, and film has to be deposited at a certain temperature sometimes. Now the physical vapor deposition, basically sputtering, where the target is used, and plasma have been formed. In the plasma, the atoms from the target material transported onto the substrate, and the film has to be deposited. And sometime in the metal oxide film, one has to be metal has been transported, and the reaction have been done. That is called reactive ion sputtering. And then thermal evaporation, what happened, and material has to be kept here, and thermally it has been vaporized, and vapor has been deposited onto the substrate. That is thermal evaporation. Now interconnect. Basically, two types of the interconnect are the aluminum interconnect or copper interconnect. Interconnect is spawned to
The slide is not visible.
Copper has an excellent electromigration reliability and 40% lower resistance than aluminum. And planarization, basically to planarization of flat surface is highly desirable for subsequent lithography and etching. CMP chemical mechanical polishing is used to planarize each layer of dielectric in the interconnect system, and it can be used in the front end process. Thangaval, am I audible? Thangaval?
Audible, sir. Audible.
Yes, you are audible, sir.
Thangaval? Thangaval, am I audible?
Yes, you are
Sir,
Yes,
audible.
sir, you
audible,
are
sir.
audible, but slide is not visible.
Okay, almost 50 slides.
You're audible, sir.
Acha, in between I have shared the screen. But it is here, it is not showing that screen is shared.
Sir, it is visible, sir. Now it is visible.
Okay. Now it is shared.
Yes, sir, it
What
is
shared,
shared.
sir? The back end
Switch
process,
into slide 4,
interconnect
sir.
back end
Slide
process,
4.
So where your internet has gone? In which slide?
interconnect back end process,
Sir, again, it is gone.
interconnect back end process.
No, in which slide your internet has been gone?
No. You are showing the slide, interconnect back end process.
So the again slide is not visible.
Yes. Large number of participants are attending this one. Am I audible?
Yes, sir.
Audible, sir. Slide is not shown. Slide is not shown. You are audible, sir.
Am I audible?
Yeah, audible, sir.
Nobody is saying.
You are audible.
You're audible, sir.
PPT is not shown here, sir.
Slide is not showing.
Yes, Thangaval.
Yes, sir. Slide available, sir. First slide. Yes, sir. Here.
Yes, in this slide I was.
Yeah. Sir.
Physical deposition, I think I have explained, but I will try to do it again. In the physical paper deposition, basically the sputtering in which the target. Am I audible?
Yes, sir.
Yeah, audible, sir. Audible, sir.
Yes, sir.
Yes, sir. Yes, sir.
Sir, please continue, sir. You continue, sir.
Sangawala, am I audible?
Yes, sir. Yes, sir.
Sir, audible,
Yes,
sir. Audible, sir.
sir.
Please continue.
Vapor deposition basically sputtering, where the target. Actually, my voice is coming onto this one.
Sir,
Now the thermal
Yes,
evaporation and thermal evaporation, where the thermally evaporated materials have to be deposited onto the sample. Next slide, please. Now interconnects, various interconnects, the backend process and front end and backend process with copper interconnect, where copper and aluminum interconnects has to be prone to void formation by electromigration. Copper has excellent electromigration reliability and 40% lower resistance than aluminum. So because of dry etching, copper is difficult. So sometimes aluminum is preferred. The planarization, a flat surface is highly desirable for subsequent lithography and etching. See, in the mechanical polishing is used to planarize each layer of dielectric in the interconnect system, also used in the front-end process. Next slide, please. Next slide. Next slide, please. Next slide. No, I'm not saying, just I'm getting your print, this one interconnect, then go to the next slide. In the after the making the interconnect, electrical test probe has to be used. Electrical test probe, after final pacification layer are applied, the entire wafer goes through the backside preparation back lab, which thin the wafer, allow the better heat dissipation and remove the stress features which could use in the bracket. Then after this one, what happened? It's a dicing will be there. In the dicing, what happened? Several sometimes defective dies will be there. So individual dies are tested to distinguish the good die from the bad ones. And this then die cutting and assembly will be there. Next slide, please. Then in the assembly, what happened? Die is wire bonding will be there. In the wire bonding, several wires have been bonded. This is connected to the pin, and after connecting it, it is final testing will be there, and chips are electrically tested under the various environmental conditions. Then what condition, and it has been used for various applications. Now in the wafer fabrication process, major associated challenges in the device processing. One is suitable and high quality wafer should be there. Dimension should be properly controlled. Process should also be controlled because various processes are involved. Sometimes in the one IC fabrication, maybe 40 or more than 40 processes will involve, can be involved, and residual stress should be minimum. Film substrate compatibility will be there. Organic residue should not be there. Parasitic capacitance while packaging should be minimized. Proper packaging and testing will be there. Now, I would like to acknowledge Director SSPL, Member of Characterization Division of SSPL, Crystal Growth Group, Shankar Dattar Mahadeva, and Organization of Faculty Development Program, ISM, IIT Dhanbad. Thank you. Any question? Any question from your side? I will answer those one.
Dear participant, the session is open for questions. If you have any question, kindly unmute.
Am I audible?
Yes, sir, you can audible. I'll let you know if there is a question.
So
sir.
any question I can answer?
Hello, am I audible, sir?
You just repeat it and I will answer this one. I will answer.
So the crystal growth
Hello,
is done by
yes.
different methods. Sir. Okay, sir. Sir, the growth of crystal is done by different methods, like floating zone method, Zokralski method, Bridgman method, and so on. So which method gives us high precision crystal growing, sir?
Thangal, can you repeat the question?
Crystal.
Actually, I have explained several crystal growth technique like Choklatsky, float zone, vapor phase transport for silicon carbide deposition, and this Bridgman technique. All the techniques can be used to fabricate the wafers.
Okay, but which is going to give us the most purest form of crystal?
Can you repeat the question? Answer question, Thangaval?
Sir, most of these crystals wafer-based crystals.
No, pardon, please.
Perhaps I suggest. I mean, the question is something like this: that which method is to be used for which application?
Which method?
Not like that. No. I'm asking you which
About the
method is
precision.
giving us the purest form of the crystal growth.
Purest crystal.
Can you write in chat box?
Purest crystal.
Yeah, he's asking about purest crystal. And my question, sir, would be that which method is to be used for which application?
Can you write in the chat box? Sir is getting not getting the answer.
The question is not. I'm not able to understand what he's asking.
Dr. Tangabir, this is Kannan. In my present next talk, I will address this issue. I have answer for this.
Okay. Okay, if there is any question, you can just write it. I'll answer you.
Yes, sir. Okay, sir.
Anything else from your side, Thangaval?
Yes, sir. It's fine, sir. That is excellent. If any question, I will forward to you, sir.
How choose the crystal growth method for one particular device?
Yes, sir.
Actually, what happened for a particular device, whereas to choose like for silicon device, float zone is very pure crystal, but the impurity is very less, and oxygen contamination is also there because it's a crystal free growth. So for the pure crystal or crystal float zone is preferred.